All right, in this video, I will be deriving the formula for resistors in series and resistors in parallel using Kirchhoff's laws. Let's first consider Kirchhoff's first law, which says the sum of the currents entering a point, so the sum of the currents in, equals the sum of the currents out. So if we have a circuit that has a source of EMF like this, and it goes around and gets to some resistor R1, passes through another resistor R2, all the current going into this point come out of it, all the current going into this point come out of it, and they flow around and complete the circuit, okay? And so the sum of the currents in equal the sum of the currents out, all the charges that sort of enter the point sort of go around it. Kirchhoff's second law tells us that the sum of the EMFs equals the sum of the potential differences. The EMF is where we are converting other forms of energy into electrical energy to put into our circuit. The PD is where we've converted that electrical energy into other forms, right, in the resistors there. And so there will be a potential difference across each one of these resistors equal to the current, which is the same everywhere, times the resistor there. And so here V1 would equal I times R1, and V2, the voltage across resistor 2, would equal I times R2. All right, yeah, I think the autofocus is trying to focus it on with my hand when I'm writing, but then once I move it away, it should sort of clear up a bit there. Hopefully it's not too bad in the meantime, or eventually there's a clear view of it. And so we have, applying this, the EMF, which would be, you know, sort of the energy per charge here, right? The voltage sort of into the circuit. E would equal V1 plus V2. Okay. And we can kind of think about the EMF here equals the voltage drop across this entire, you know, so both resistors, right? Like there's a potential difference or there's a voltage drop across both resistors equal to the EMF. And so like this EMF is equal to that total sort of voltage drop V. Okay, so V, which is the voltage drop across both, equals V1 plus V2. And Ohm's law tells us that V equals IR in general, like we saw up here. And so the combined voltage drop, IR, across the entire circuit is equal to I times R1 plus I times R2. And here we could, you know, sort of factor out the common I or sort of divide by I, however you want to think about it. And so the combined resistance for resistors in series is just equal to R1 plus R2. And we could imagine having other resistors in series with this, it would just continue to sort of sum these resistors. And so that's how we can derive the equation for resistors in series. For resistors in parallel, we consider current I entering a node that then travels in one direction this way, I1, which will pass through a resistor R1 and then get to a node. The current goes this way, I2, and note that that direction opposes the direction of this current, passing through another resistor R2. All right, to meet back up over here where the current, you know, once again, is I. And so we still have Kirchhoff's first law, I equals I1 plus I2, except for we have to add negative I2 because the direction of this current, you know, is opposing sort of this one here, okay? Now, the voltage sort of across these nodes, all right, is zero because there is no source of EMF inside of this loop, okay? So we say that the voltage sort of across here is zero, all right? It's just a loop with no EMF. All right, so we've got from Kirchhoff's second law, the sum of the EMFs equals the sum of the voltages. The sum of the EMF is 0 because there is no EMF inside of this loop. This equals the potential differences across the resistors. And so if this direction is positive, then we'd have I1 R1, okay, the voltage drop across this one. And then we're adding the voltage drop across here. It's the sum of the voltages, but we're actually adding the negative current, right? Because it's going opposite direction. So I2 R2. And so the difference of these voltages equals 0. And so they must be equal to each other. I1 R1 equals I2 R2. And remember that I times R is voltage. And so voltage 1 equals voltage 2. The voltages sort of across each one of these are equal to each other. And this sort of shows that the voltage is the same across parallel branches. Okay, the voltage is going to be the same here. If we consider Kirchhoff's first law, I, the current going in, equals I1 plus I2, sort of in general, right? Keeping in mind that sort of this is going in the opposite direction there. We can see that we've got if V equals IR, then I equals V over R. And so V over R for the entire sort of loop there equals the same voltage V1. So V1 and V2 are the same. Let's call them, V for voltage over R1 plus V over R2. And again, because voltage is sort of the same everywhere, we could, divide by V, sort of factor out that common V, and we get this expression that 1 over R, the resistance of the entire circuit, is equal to 1 over R1 plus 1 over R2, right? And again, we could sort of add as many resistors as we wanted to in parallel. We sum the reciprocal resistances to equal the reciprocal of the circuit resistance for a parallel circuit. And so this is the equation for resistors in parallel. And this is the equation for resistors in series. All right, so got a chance to focus there. All right, so that is the derivation of the formula for resistors in series and in parallel based on Kirchhoff's laws.